Well, so apart from what we have already done, we were trying to find out the departure functions from the PVT behavior of gases. Now, apart from PVT behavior, we can also use the compressibility factor chart for finding out the departure functions. For that, we need to just reorient the equations which we have derived. We just need to write them in terms of Z and TR, PR, etc. How to do this? Let us see. V is nothing but equal to ZR T by P. Del V del T at constant P, then we can write it down as ZR by P plus RT by P del Z del T at constant P, or in other words we can write it down as R by P Z plus T del Z del T at constant P, isn't it? So, in that case, delta of delta H star delta P at constant T, what is this? This is nothing but, if you simply substitute this equation here, then what do we get? Instead of V, we are going to write ZR T by P and then minus T, the expression for del V del T at constant P. What does it reduce to? ZR T by P minus T R by P Z plus T del Z del T at constant P. Agreed? Or in other words, this reduces to ZR T by P minus this term is also ZR T by P minus RT square by P del Z del T at constant P. Or in other words, this can also be written down as delta H star on integration we get, this is nothing but equal to minus R integral minus RT square integral 0 to P del Z del T at constant P dP by P, isn't it? And therefore, this equation we can also write it down in terms of reduced parameters like minus R TR square TC square for T integral 0 to PR del Z del TR TC dPr PC by PR PC, isn't it? And then what do we find finally? We find that we have expressed delta H star in terms of minus R TR square TC integral 0 to PR del Z del TR at constant PR dPr by PR. Agreed? So, therefore, from this we find we could express delta H star in terms of TR and PR, and so therefore, if we know Z in terms of TR PR, we can substitute it and we can find out delta H star. For using Z, you will recollect that we had already shown you the use of compressibility factor charts which express Z as a function of TR and PR. Just in the way we have expressed delta H star, we should be in a position to express delta S star as well. How to express? In the same way, we are going to substitute this expression here and we are going to work it out. This gives minus R integral 0 to P Z minus 1 by P plus T by P del Z del T at constant P dP, isn't it? And this also we can write it down as R integral 0 to PR Z minus 1 plus TR del Z del TR constant PR whole thing dPr by PR. So we can also find out delta Z star and delta H star in terms of Z TR PR. We can use this compressibility factor charts to find Z. Then we can integrate Z as a function of TR and PR, Z as a function of TR at constant PR, and we can very well do this. But there is something more interesting if you observe the equations that I have written down. The equation for delta S star and the equation of delta H star, I rewrite it just for your convenience. This is integral 0 to PR del Z del TR at constant PR dPr by PR. Observe these equations carefully. What do you find? You find that suppose you can express this equation as delta S star or else delta S star by R, then what do you find? You find the right hand side, it's just expressed in terms of reduced coordinates. So what does it show? It shows that this parameter delta S star by R, this definitely obeys the law of corresponding states. In the same way, if you can express this equation of delta H star in this way, you find again the right hand side, it contains only the reduced parameters and Z and nothing else. What does it imply? It implies that these two terms, delta S star by R and delta H star by RTC, they definitely obey the law of corresponding states. So therefore, we need not refer to the compressibility factor charts that I have shown you here. We should be able to generate identical curves using delta H star by RTC as a function of PR and TR. We should be able to generate delta S star by R curves as a function of unique functions of TR and PR. And this has been done by a large number of researchers so long, and the curves, they are of this particular form. These curves, they have been generated by Edmister, and they are used very frequently in the hydrocarbon industries in order to estimate the reduced enthalpy departure function as a function of reduced pressure and a function of reduced parameter. Okay. And in the same way, graphs have also been generated for the entropy departure function. Now, it is important for us to remember that just like the compressibility factor chart which we had discussed, we had found out that the two parameter law of corresponding states, it is not very accurate, and we often resort to the 3 parameter law of corresponding states. For the 3 parameter law, what do we need to do? We simply express Z as a function of Z0. This is for simple compounds or simple molecules, and then we incorporate a correction using a third parameter which is the eccentric factor. So therefore, if we wish to incorporate this and express delta H star by RTC as in terms of the 3 parameter law of corresponding states, that also we can do in this particular case. For that, what we need to know, we just need to substitute, instead of Z, we need to substitute Z0 plus omega Z1 and find out the relevant equation. What's the equation? Let us see. The equation becomes this becomes minus RT square by TC integral 0 to PR del Z0 del TR at constant PR dPr by PR. We are simply substituting that and elaborating the equation by TC integral 0 to PR del Z1 del TR at constant PR dPr by PR. Or in other words, we find that we are in a position to write the enthalpy departure function in terms of something like delta H star by RTC as delta H star 0 by RTC plus omega, this was already minus omega. So therefore, plus omega into this particular term which is H0 minus H of 1 by RTC. For this term, it can be written down as omega TR square integral 0 to PR del Z1 del TR at constant PR dPr by PR, right. So therefore, we find from here the 2 parameter expression, it is nothing but TR square. I'll just write down delta H star by RTC 0. This is nothing but TR square integral 0 to PR del Z0 del TR at constant PR dPr by PR, and delta H star by RTC1, this is equal to TR square integral 0 to PR del Z1 del TR at constant PR d. Well, I'm confusing the small and all of these are small alphabets, dPr by PR. So therefore, just like we had discussed for the case of your the compressibility factor, in this case also we find that for greater accuracy we need to incorporate not only the 2 parameter but also the 3 parameter law of corresponding states. A similar exercise can also be performed for the entropy correction or the entropy departure function as well. In that case also, if we proceed in this particular way, we find that delta S star by R, it can be expressed as 0 to PR Z0 minus 1 plus TR del Z0 del TR at constant PR, this whole thing dPr by PR plus omega integral 0 to PR Z1 plus TR del Z1 del TR at constant PR, whole thing dPr by PR, where this particular part, this whole part, it is nothing but delta S star 1 by R, and this part it can be written down at delta S star 0 by R. Now several charts have been proposed, as I have already discussed. There are charts by Edmister, and one can refer to those charts by going to the book of Edmister. We find that there are enthalpy departure functions, there are entropy departure functions for 2 parameter as well as the 3 parameter law, the 3 parameter corresponding states, and usually we prefer the 3 parameter because 2 parameter model, it was anyhow not very accurate for predicting compressibility factors. So naturally it fails much more for the case of enthalpy and entropy departure functions as well, right. So these are the 2 types of charts which are available. The initial charts which I had shown, they are for Edmister, they are primarily used for the hydrocarbon industries. There are also certain other charts which have been proposed by Lee and Kessler. These charts can also be used. You can very well see that they have the 2 parameter and the 3 parameter enthalpy as well as entropy departure functions. You can see they have been expressed for lower values of reduced pressure and higher values of reduced pressure. One can very well use them and they can find it out. Okay, we can do a 1 or 2 problems regarding this so that you can get a better feel of it. For example, suppose I tell you that we are interested to find out delta H star and delta S star for methane, say, okay, for methane at 32 degrees centigrade and say 9.28 bar, and I tell you to use Edmister chart for this. So what are you going to do for this? You are required to find out the enthalpy and entropy departure functions for methane at 32 degrees centigrade and 9.28 bar, right. So let us go to the Edmister's chart for this. The Edmister's chart are this, right. Now for methane, the first thing that you need to do, you need to find out Tc, Pc and omega, right. What is Tc in this case? You can find it from any standard table or etc. Pc is going to be 46.41 bar and omega, this is going to be 0.011. Once you know this, you are in a position to find out Tr. Remember, this Tr and Pr, they should be, these are in terms of Kelvin. So therefore this also has to be converted to Kelvin. Now there is one thing which I would like to tell, the problems you tend to make mistakes just because you do not consider the right units. It's very important when you are working with pressure. Suppose you are using Anton's equation, very frequently they are given in torr. So therefore the pressure which you are going to use has to be in torr. when you are working with temperatures, see at it for in which unit they are given. So these things are very important if you want to arrive at correct answers for not only for thermodynamics, for anything for that matter. So therefore this becomes 305.15 by 190.7, which is nothing but 1.6. In the same way you can find out PR, it's going to be 9.28 by 46.41, which is equals to 0.2. So therefore you need to find at PR equals to 0.2 and TR equals to 1.6. Let us go to the enthalpy charts. You find out for this particular situation you are going to get from here. From here, if you can locate your PR equals to 0.2, it's here somewhere, and PR is equals to 0.2 and TR equals to 1.6. This is the line. So if you follow this line and to come to 0.2, you find out that your delta H star 0 by RTC, this whole thing becomes 0.085. Check it up for yourself and find out. Then if you go to the next curve, then you are in a position, the next curve if you go, then you are in a position to find out delta H star 1 by RTC. Find it out, you are going to get this is 0.01. Similar fashion, if you find out delta H star 0 by R, read it out, it's going to be 0.032. Delta H star 1 by R, this is going to be equal to 0. You can use these particular graphs and you can find them out. Now once this is available, you can find out delta H star by RTC. It's just going to be this plus omega of this. So if you calculate it as 0.085 plus 0.01 into 0.011, then from there you find the value is going to be 8.511 into 10 to the power minus 2. And from here, what is the value of delta H star then, which you are required to find out? This is nothing but minus 0.135 kilojoules per mole, right? So therefore in the same way, if you proceed with delta S star by R, you have got, so therefore we find out that delta S star by R, this is just this value plus omega of 0. So naturally this reduces to 0.032 only, which gives you delta S star as minus 0.266 joules per mole Kelvin, right? So therefore in this particular way you can take up a few other problems and you can find it out. For example, suppose take up the problem for propane. Instead of methane, suppose I tell you to take up the problem on find out delta H star and delta S star for propane at 60 degrees centigrade and 17.03 bar. You can use the Edmiston's chart for doing this. I'll just give you the answers. You compare and to just see whether you could do it or not. Delta S star will be minus 4.511 joules per mole Kelvin, and the value of delta H star is going to be minus 2.163 kilojoules per mole. Just try it out and see what you are getting. In the same way, for using Lee-Kessler chart also, suppose I tell you that for the same propane you do it using the Lee-Kessler chart. For using the Lee-Kessler data, naturally we have to go to the correct graphs for this. These are the graphs for Lee-Kessler data. Now here also you need to know the value of TC and PC. So TC in this particular case for propane it is 369.9 Kelvin, PC this is equal to 42.57 bar, and omega it is 0.153. Provided these are given, then you are in a position to find out well 60, yeah, you are in a position to find out TR here. TR is 0.9, PR this is equals to 0.4. So from these particular graphs you find that for PR equals to 0.4 and TR equals to 0.9, you cannot use this graph, you have to use this particular graph, right? Now here you can use this graph, sorry. So for this TR equals to 0.9 and PR equals to 0.4, if you read it out, you find that the value in this particular case it's almost equal to 0.6. It's more accurately 0.596. You can take it as 0.6. So therefore you find that delta H star 0 by RTC in this particular case it's 0.6. Again if you go to the next curve, you find that delta H star 1 by RTC, if you read it here again for 0.4 and for 0.9, you find it is about 0.75, right? So therefore from here you will be in a position to calculate delta H star by RTC. It is just this plus omega of this. So therefore this becomes 0.7109 or 0.71 you can take, from where we can calculate delta H star to be minus 2.186 kilojoules per mole. R in this particular case, since we are dealing with joules, this is going to be 8.314 and the value of TC it is 369.9, which I have already mentioned. Same way, if you would wish to calculate delta S star, we can do it as well. Here also you need to go from 0.4 to 0.9 and you can see the value is about 0.463, isn't it? So therefore delta S star by R0, this is 0.463, and if you are going to calculate delta S star 1, again from 0.4 to 0.9 it's about this particular value it's about 0.744 something, yeah, 0.744. So therefore 0.463 plus your 0.153 into 0.744, that gives you delta S star by R, and which is nothing but 0.5768. Multiply it with the value of R, which is 8.314, and finally you get the value as delta S star equals to minus 4.796 joules per mole Kelvin. So in this particular way you can try a large number of problems and you can get yourself conversant with the usage of these charts. Now before I end, it's also important to just have a brief discussion on the prediction of departure functions using virial equations of state. What is the virial equation of state? We know this is Z equals to PV by RT. For low to moderate pressures, we truncate it after the first term. This can also be written down as BPC by RTC, PR by TR. Remember one thing, this is applicable for low to moderate pressure. This is something important. So therefore what is V equals to, this is RT by P into 1 plus BP by RT, which is nothing but RT by P plus B. Accordingly, what is del V del T at constant P? This is nothing but del P del T plus R by P. Accordingly, what is delta H star that we get from here? The value of delta H star and the value of delta S star. What are these values that we get from here? These particular values are, this is, just substitute and find out B minus T dB dt into P, and delta S star, this is equals to minus P dB dt, right? So therefore, and here also you can express B in terms of B0 and omega B1. You can also express B in terms of RTC by PC, B0 plus omega B1, and you can use the 2 and the 3 parameter law. For this class, it is just sufficient to to know that delta H star and delta S star, they can be defined in this particular way. So therefore, these are the ways by which you can find out the properties using the PVT behavior of gases or the cubic equations. You can use the compressibility factor chart, you can use the Virial equation of state, and apart from these were the ways by which you can do it using the PVT behaviors. Apart from the generalized equations of state or the generalized compressibility factor charts, we also have some particular figures, some particular tables in order to find out or predict the thermodynamic properties. One such common table is the steam table, which you are already aware of. There are certain other charts also available for finding out the properties, particularly enthalpy and entropy, instead of going through the detailed calculations that we have said. A few of these are the pressure enthalpy diagram, which is shown here. This particular diagram is shown for nitrogen, and here if you observe, you find that the entropy curves are given, the pressure and enthalpy are given, and we also have the specific volume data and the temperature data. So therefore, it contains a large number of data, and you will be in a position to find out the enthalpy and entropy. We can have such particular charts for other gases as well. Then there are also the typical temperature entropy diagram and also the enthalpy entropy diagram, which is very easy. And regarding this enthalpy entropy diagram, this is known as the Mollier chart. This is very convenient because from here we can find out enthalpy, we can find out entropy, and since it contains constant pressure lines, constant temperature lines, as well as constant quality lines in the two-phase region, so therefore this gives us a large amount of information, and this is a very popular chart which is used for predicting the properties of gases. So with this we end the estimation of properties of pure component gases or mixture of gases where the mixture behaves as a pure component, right. After this, we are going to study the properties of mixtures, and we are also going to extend our discussion to homogeneous open systems and heterogeneous closed systems. So with this, we close our discussion on homogeneous closed systems. We have discussed the estimation of properties and the concept of thermodynamic potential and the concept of chemical potential. We are going to use this further in our discussions on phase equilibrium thermodynamics. Thank you very much.